Thank you, Fred. Hi, I'm Anton. I work on analytics at WhatsApp, and I'm going to be talking about a system that we've been working on. And hopefully, by the end of this talk, you will have enough information and knowledge to be able to build something like that in your own environment. So that's why it's called Step-by-Step Guide to Building an Application Analytics System. So a little bit about our problem. So we have quite a few users, and WhatsApp is a mobile messaging app, and the app is deployed to extremely diverse environments. So we have 7 different platforms, tens of thousands of devices, and the users use the app in a very unpredictable way. So it's very hard to judge how the app performs in the field without getting some data from the app itself and then analyzing it to see if we can make some improvements, find some bugs, and overall improve the app and user experience. So as I said, we've been working on a system that's internally it's called WAM, WhatsApp Application Metrics. And what makes this problem challenging is that with 500 million active users, give or take, each sending about 1,000 data points, we're talking about 500 billion data points a day. And with each taking 10 bytes, conservative estimate, it totals at 5 terabytes per day. On the other hand, what makes this problem sort of easier is that it's an internal tool. It's not an enterprise project. It's not even open source, well, at least yet. So, and our users are engineers, so we can take a lot of shortcuts here. And before I move forward and explain how it works and what it does, I would like to show you a quick demo. So the thing that you're looking at here is called the IPython notebook. It's an interactive computing environment written in Python. And it's used by lots of people all over the world as an interactive computing environment. Basically, you can write Python code in what's called code cells, and then get results of your execution displayed in various formats. And it can be text, can be an image, can be a set of images, can be even a video or formatted HTML. So I'm going to run through a couple of examples to show about a couple of real use cases. So what you're looking at here is and the overall system is divided in 2 parts. There is an analytic database that stores data, and then there is a query interface on top of it that allows us to source data in this IPython environment. Then the results of the query are cached in memory, and we can run all sorts of post-processing on it, including visualization, transforming data, and basically lots of stuff. So, what you're looking at is a query. It kind of looks like SQL, but it has a slightly different syntax. But what we're doing here is we're selecting some data from the table named field stats, and the actual data that we're requesting is to build a histogram of application launch time, and we ask for 1,000 bins, and the range of the histogram is from 0 to 30,000 milliseconds, which is 30 seconds. And we do it, and we ask it for the S40 platform. And the match expression here basically means the full day of the day before yesterday. So the equal sign is corresponds to truncating the timestamp by the closest D unit. And then the usample means get this data for at least 10% of users, and UTC is basically a time zone. We're interested in UTC days. So let's run this query. It returns almost instantaneously, and it prints a tabular representation of histogram, which is basically, you can't look at histogram in the tabular representation when it's returned. But the thing to note here is basically the histogram was built by the query using over 4 million data points. So another thing that we can do with it is we can plot it. So we can ask, and let me expand the area a little bit. So we can plot a histogram. And this is a high-resolution histogram. If you remember, I requested 1,000 bins. And we can do a lot of interesting stuff with it. For example, we can, and generally what we want to see here is we want this time, application start time, to be small. So we want the histogram to be skewed and towards 0. And we're also interested in not seeing this long tail. Over here on the logarithmic scale, you can see there's a lot more prominence, so you can actually see something. So another thing we can do, sometimes it's useful kind of to look at, let's see if I can get it under control, at the histogram at a lower resolution. So I can ask the system to lower the resolution of the histogram and just basically do some styling so that it looks like a real histogram. And it's also possible to zoom in and zoom out to a specific range or sub-range of the histogram. So, but it still doesn't explain why we're seeing. So one interesting thing here is that there are humps, right? So the distribution is multimodal. That's interesting. So let's try to look at why is it happening. And I'm gonna run the second query, which is similar to the first one, but I'm gonna group the histograms by a client version, by application version. So I just did that, and I got a bunch of histogram returned essentially for every S40 client version we have out there. And on the next line, I'm going to just pick the top 3 by absolute count. So there's some good defaults for sorting and selecting top elements. And then I'm going to just print a histogram again, and you see a great plot. And it kind of feels that the distribution for the top 3 mostly used WhatsApp version on S40 are kind of similar. But so we don't get much, but in order to confirm that similarity, we can move them to a single plot and then recalculate counts. And they're to turn the absolute counts in the histogram bins into relative proportions. And indeed, the distributions are fairly similar, so nothing stands out here. So let's run a similar query, but this time we segment or group by histograms by device name. Okay, so the query returns, and we will plot the top 5 device names by the number of users, by usage. So, and what we can see here is pretty interesting. So now it's pretty clear that where that multimodal distribution comes from. And if you ask S40 engineers, they will tell you, well, yeah, those devices actually vary a lot in terms of how fast they are, like in terms of CPU and resources available. So that's not a surprise. And we can do even this and kind of see an overlaid view of that. And So that's a very small example that shows like very small portion of the capabilities of the post-processing and the querying capabilities that we have. So let's go back to the presentation. So in our experience of building and using it, it turned out to be a pretty powerful tool for doing application analytics, but it's also very simple in the way how it's built. So, and I truly believe like any competent engineer should be able to do something similar in reasonable time, even at scale. So in the rest of the talk, I'm going to talk. I'm going to go over these basic components and describe how they work. And I won't be able to talk about collection because it's a very like company specific and it's messy and it's not a nice generic thing to talk about. So where does WAM fit if we compare it with popular tools? Probably everybody uses systems like Graphite and printf-style text logs. And we know that Graphite is extremely powerful. It's actually very easy to analyze data because once you get data in, you immediately get it visualized, and you can use all sorts of functions to work with it. Text logs, on the other hand, but Graphite is kind of limited in the sense that it only works for time series. You cannot do histograms with it. You cannot do things that I've just demoed. Text, on the other hand, the printf-style text logs, they're like you can log anything. Like they're extremely flexible in terms of what they can represent, but getting data out of text logs is a major pain. It really doesn't scale. Using tools like grep and Perl doesn't scale past a certain point. Yet it's still valuable to look at text logs sometimes with bare eye. So WAM is not a replacement for those tools. WAM is but it's an attempt to get something more flexible than strictly time series type of tools and a lot more usable than just raw text logs or raw text logs passed through ETL and kind of made available in some other structured form. So to be more specific, in terms of comparison with Graphite, so data that can be stored in one may be looked at time series or may not be looked at time series. It is stored at full resolution, unlike in Graphite. There is an arbitrary number of dimensions. You cannot use many dimensions with Graphite. The system will just blow up. It's not designed to do anything like that. And then the interface to the analytic part of WAM is essentially SQL, and then you can leverage all the power of PyData stack to do analysis on aggregates and samples. So the analytic part, the analytic database part of WAM can be represented as described as a fast parallel SQL-like queries of a distributed and sparse log. And that brings me to the second comparison with, this time with data warehouses. Data warehouses are traditionally used for fast analytic queries, and modern data warehouses scale extremely well and things like that. So WAM is kind of limited compared to them in the sense that it doesn't have full SQL, like no join subqueries. It doesn't have many tables. Like you can join across tables. You can have relationship between them. And it's not as optimized as data warehouses. Multiple query plans, intelligent CPU scheduling. It's super optimized data format. It's not what WAM is currently has. But it has two amazing properties. First of all, in order to use it, you don't need an ETL. There is no loading step involved. The data that comes through the collection system goes straight into WAMP, gets stored, and immediately available for querying. Now, and then the dynamic, what I call the dynamic schema evolution. Adding fields, adding columns is a no-op, essentially. It's a logical operation that gets picked up by the system, but it has no actual like management, schema management involved. There are no database commands to run, sort of. So the data model, and this is the data model when it comes to consuming events from the application. Basically, one can take in any event that can be modeled as a set of key value pairs. And the key part of the key value pair represents some kind of field ID, symbolic field ID, and the field value is essentially some value of one of the primitive types we support. So here's an example of a typical event that we log through the system. So we have fields like event ID, which in this example corresponds to media upload. Then media upload type, which could be one of photo, video, audio. Then media upload result, which can be OK, duplicate, or error. And then we have two measurements, the media upload size and the media upload time in milliseconds. So pretty straightforward, right? And it's useful to think, and it's conventional to divide the set of fields that you log into analytics system into two subsets. One are called dimensions, and they're usually categorical fields that are used to describe the actual measurements. And then the measurements themselves. They're called measures. But that's not the full story. So what makes our problem a lot harder is that we have other dimensions. And every event that comes from the mobile app has those dimensions reported as well. So we have timestamp of each event. We have user ID, which is a very high cardinality dimension. We have 7 platforms. We have application version, operating system version, device name, countries, and information about networks. And this list is not complete. So what do we do next? We actually define it. We actually define a schema. And we do it in a very simple and straightforward way. We have 3 files. Dimensions.json, measures.json, and enums.json, and they have very simple format. They're essentially a list of small JSON object, and each object describes a field in case of dimensions and measures, or an enum type. And here you can see an example of defining definitions of media upload type and the media upload result dimensions. For example, media upload type has an enum type, media type. Then it has a unique code ID. And some other properties, one of which is just describing what it is. So the media upload type is a field ID. It must be unique across all fields in the system. And the codes are also unique across all fields in the system. So and the supported primitive types are string, enum, timestamp, integer, double bool. So pretty straightforward, limited set, no nesting, flat namespace. So how do we manage the schema? So we put those 3 files in a Git repository. When somebody needs to make a change, they make a change, add a field, for example, or deprecate a field. Then they push changes to the central repo, and then they ask the client to tell the system to update. They call the client to update the schema in the system. So, and that's pretty much it. And then the system pulls the latest version of the schema from the Git repo and does the right thing on the server side. Okay, so we mentioned about SQL, and SQL works on top of relational data. So how does the schema translate to relational interpretation? It's very simple. So we have a table created implicitly for each application, and that table has all the measures and dimensions defined in the schema. Just like that. So there's no actual create table or alter table, but it's implicitly there. Okay, so moving on to the storage format. There are 2 traditional approaches for storing structured data in relational databases. One is row-based, another one columnar. I'm not going to go deep into details, but columnar is the one that is actually used in analytic databases. So if you imagine a table and vertically divide it in columns, and then take each column, compress it, and serialize it into a file, and they take another, and then do it with every other column. So you kind of linearly serialize them in the file, then add some indexing structure, store some metadata about like dictionary encoded categorical variables and things like that. You get a columnar format. It's highly compressible. It allows you to fetch only necessary columns when you actually do the query. So if your query takes two measures and group bys, aggregates two metrics and group bys by some other third one, so you only need two columns. And if your database stores, I don't know, 100 columns, which is not common even in typical data warehouses, like they're not touched. So overall, it's an ideal approach. And you should definitely look at that and probably do that if you're serious about building an analytic database. The problem is that this data format is not exactly trivial. Like, it may take a while to get it right and perform well. So I'm simplified a bit. There's a lot more complexity that goes into columnar representation. So instead, we didn't have all that time, at least up to this moment. So we may look into columnar later. So what we do is we store data in so-called long format. And it essentially mirrors the format that the data comes in. It has each event is represented as a sequence of non-null field, and each field is encoded as a combination of field code and field value. This means you don't. It's row by row, but you don't get. You basically compress the sparse representation into dense, long representation, and so primitives, and then there's a pseudocode that describes, you can see a pseudocode that describes how it's actually done. For primitive types, it's basically a tag that says, well, this is a primitive field of a primitive type, then the field code, then the primitive value itself. And for the dictionary encoded strings, we do, like, the first entry corresponds to the actual dictionary entry, and where we store the field code, the unique string ID in the stream, then string hash for optimization purposes, and the actual string payload. And the second one actually references it. So once you have one string in your system, in your stream, you don't have to repeat it anymore. Standard dictionary encoding practice. Just and of course, you need an end of record marker somehow represented, because you serialize record one by one, and you need to basically know when one record ends and another one starts. So typical practice used in columnar databases is called run length encoding. So if you have a column value that spans several consecutive rows, that's called a run. Basically, it can be compressed by taking the value itself and then specifying how many times it repeats, it repeated. That's called the run length. And you can represent it in that format and further compress it down. So it's fairly compact, is simple and very easy to implement. It's definitely slower to read than columnar format. Now, on top of it, we use general purpose LZ family compression algorithms called LZ4. It's generally faster. We found it to be generally faster than Snappy and much faster than LZO. And it has a high compression mode, which gives us 6:1 compression ratio in our case. Also very nice, has a very nice tool in it. It comes with a default framing format. Basically, it lets you not care about checksums. It does it for you, and other options as well. So how do we store that data? We write records in the describe format to a log. up to a certain threshold. It's determined either by size, when the size of the log reaches a certain threshold, or time reaches a certain threshold. Then we rotate it. So when we rotate it, we compress it, name it with the SHA-1 of the contents of the log, and compress it with LZ4. And then the next step is to move it to a permanent storage. So onto the query language. I mentioned a couple of things about it. I won't go too much into details. Basically, it's much, you can see a SQL query corresponding to the WAMP query at the bottom, and generally it's a lot longer. So the main motivation for us is to make it shorter. It's actually for interactive use. We type it a lot in the shell. We use it in the IPython environment, and it helps with typing in general, compresses the syntax. So there shouldn't be like really, it's pretty obvious that it mirrors SQL semantics, just adds a couple of things on top of it and a couple of shorthands. One of the things that we specifically added was sampling, including random sampling and histograms. And the language is overall extensible. Very extensible. So we add features and small tweaks there all the time, and the tooling makes it really easy to do so. So finally, the query system. So there is a query compiler that takes the schema and the query string and turns it into a C program. Then the C program is compiled with a C compiler and linked with a small C runtime. You get a program that you run in parallel on data stored in files in the local file system. Then each instance produces temporary results. Then at the end, you just merge results and write output in JSON format into the output file. So that's what the query system does in a nutshell. The query compiler is written in Erlang. So the whole parsing, in order to parse that language, we use a tool called Piki. It allows us to describe the query language syntax in a high-level declarative way. So, and the only thing that we need to do after that in order to parse it is to call this string. So it saves a lot of typing, and it validates a lot of syntax for us, and you don't have to think about it when you're adding extensions and things like that. Then the analyzer and code generation is actually, it generates a tiny C program. So the runtime, really quickly, nothing super interesting. If you think of it a little bit, you will be able to get the same result first time you try. So you have to read data, write output, do JSON formatting for the results. You do hash table, you can do standard SQL. You represent a histogram as a fixed size C array because you know the range and the histogram bin width. Then you do a bunch of, you can do standard stuff for order by, and of course you use standard STL stuff for random, just wrap it. And then string table, symbol table is represented as a hash table, and the group by is also as a hash table. So the only interesting thing is for count distinct, we use something that's called hyperlog log as a probabilistic algorithm. Years of research went to it. It's super nice if you want to count efficiently with a small configurable error up to like a billion unique elements. And it allows you to do that with a really small stage, just a couple of kilobytes. So with that, with that tricks, you should be able to get your query to process input data at a rate of 1 or 2 gigabytes per second. So, and this is actually how it works. Like the single thread is not actually used, but just an example. So you send pipe file names to the reader, which is just a wrapper for LZ4, and it pipes the uncompressed output, the WAMP query, which stores results in the file. For the parallelized version, we actually use GNU parallel. It's written in Perl, but this is all you have to do to get the parallel query working. And basically, this spawns n workers and then distributes the load across them. Then all those workers store intermediate results, and the same program being called an intermediate results produces the JSON output, the combined JSON output. So the protocol, if you're, the API or the database protocol, basically there's a tool called PKRPC that allows you to create JSON over HTTP define services really quickly in Erlang. Again, you use a high-level definition language, and everything thrown at you as a HTTP post will get validated and turned into Erlang term. And this is all you have to do inside. You have to process it, and then you turn it into a record, and the system does it. The transformation the other way around returns JSON to the user. Super simple. So if you want to do a shell, you go with SSH with key-based authentication, and have a program sitting behind SSH that reads a line, includes that line into a HTTP post call, prints output to standard output. And that gives you a pretty powerful shell, especially if you use something like a read line wrap, which gives you line editing, history of commands, tab completion, and everything else. You spend a couple of hours on it, and you're done fiddling with parameters. So, like if you think of it, suppose you have log files, and that's basically mirrors what you usually do on the server, right? So you just have a bunch of log files in the var log directory or something like that. So if you have them written by WAM and just keep them there, put the API in front of it and the query system in front of it, you can actually do a pretty sophisticated analysis using the analytic queries, the SQL-like queries on those logs, just like that. And storing those files in the local file system may be good enough. Even if you were to store a terabyte with each file taken for 64 megabytes, you will end up with only 32,000 files, give or take. So any modern file system should be able to store that pretty easily. So that's basically those components alone get you already pretty far ahead. Like it's really fast, and it scales well, and it's really powerful. So I'm gonna have to. Do I have time for questions? Okay. So I'm gonna go really quickly. What else you can do with the local file system without going distributed file system? So you can use file system as an index. You can basically partition all your data into 1-day intervals or whatever intervals you decide, and add that under some extra directory. You can do application indexing as well. For example, we kind of index everything by platform, but this is very application specific, and it's not automatic. You have to do something in the query system in order to support that. And the worst part of it, if like you have to decide about it up front, and you're not going to be able to change that. So, and then if you have multiple applications, multiple data streams, you just add another directory for tables. So I'm not going to have time to talk about the distributed storage. Actually, there is a very simple way how you can provide the distributed storage on top of all this. And have this data processed locally, and then aggregate query results and such. So I'm going to talk really, really briefly about the UI and post-processing. So the IPython notebook is a fantastic tool, and if you're not using it today, I'm pretty sure you're going to be using it in a couple of years. The project is super active, and it's amazingly useful. It's an open source project. There are also great Python libraries that we use. We didn't have to have plotting, didn't have to write our own plotting. So, and One of them is pandas. It basically provides a fairly efficient in-memory representation for further like pivoting, slicing, and dicing, manipulating, running a bunch of aggregate functions, time series, and manipulation, and so on. Then the matplotlib is a de facto standard in the Python world for doing plots. And then there's a Seaborn that we currently use for a little bit more advanced stuff. So one point about the plotting libraries, I actually looked at various JavaScript charting libraries, and they all pale in comparison compared to matplotlib. So matplotlib is a scientific plotting library, and I'm so happy that I decided to go with it instead of like various charting stuff, because you learn so much how things can be done, and it has so many features that you wouldn't be able to find anywhere else. The problem is that it generates PNGs essentially, and they're not interactive. So we would like to have more interactivity in the UI. I've showed you some of the JavaScript widgets and sliders. These are something that's built in the IPython environment. You just have to call interfaces in order to use them. But it would be also cool to work directly with the graphs and have brushing, tooltips, panning, and zooming, and things like that. We're also going to be looking at more powerful visualization techniques, and there are many tools that we can use in the Python world alone. And so there are some references. I'm not going to keep them on the screen, but they will be available in the presentation. It's basically the tools that we use and some of the references to the similar systems and some of the inspirations we took when we're building that system. So with that, I have to wrap up. Thank you for listening. Yes?
Yeah, the data that comes in, if you sort of show the dimensions and the measures, is there a time series element to that too, or is it just
yeah, sure.
everything gets timestamped as well?
Yes, absolutely. Everything that comes in has a timestamp. You see the first thing?
Okay.
So that's every event is timestamped. Not always useful, but it's great to have.
The code generation. So you specify that query begin. It's like a DSL.
Yeah.
Then you have to translate it to the C program.
Exactly.
So there's things like select what group by.
Yes.
Well, average, whatever.
Yes.
Whatever. So how is that implemented?
It's a fairly simple code generation if you think of it. Like if you never thought of it, I encourage you to think, and it's actually pretty simple. So you actually go row by row, you materialize a row, and then you decide what to do with it. Some of the fields are going to be aggregated, some of the fields are going to be used as group by key. And the whole program with all bells and whistles, like the compiler stuff, is probably the most complicated part of the system, but it's still like 5,000 lines of Erlang code, and it's really straightforward, I must say. It's just for data manipulation, all the stuff that takes some code. And the overall system, I have to mention it, it's well under 15,000 lines of code.
So Anton, can you say a word about performance? You mentioned that you get 5 terabytes a day, and like you do something between 2 gigabytes. It's like 5,000 seconds.
So excellent question. Well, first of all, we're not quite there yet. That was an estimate. So we're about like 5 to 10% of the 5 terabytes and the event volume right now. And then, if you notice, there are lots of pipes involved, right? So basically, on a 32 virtual cores machine, we can process data at anywhere from 6 to 10 gigabytes per second. And I think that's like really low. So I just haven't had a chance to spend time on finding those bottlenecks, and some of them are like really obvious. It should be way higher.
So what do you think overall about scalability? So I mean,
So we're going to scale the number of hosts, obviously. And also, one interesting thing, we have several sampling capabilities. So we actually don't have to go over all data to get some to get some useful information. So if you want your queries to return something fast, you do sampling. If well, we may start looking eventually at columnar formats and things like that, but so far performance has been sufficient. So it's like we do best effort optimization, and I've been more focusing on the front end part of it because honestly, it's been the hardest part. It's like it's a human interface problem, but it's a difficult one. Like it's open-ended. How to scale an analytic database, you can read about it, but how to provide a nice, friendly interface to working with data, it's not obvious. Like data scientists use those low-level Python libraries all the time, but they're not really that accessible to people who don't want to do like very low-level, like R-style analysis.